All right, day 2 on parametrics. The first question at the top of the worksheet is just a warm-up review of what we did last week. We're going to start without the calculator. Remember, a parametric set of equations means there's 3 variables. To determine x and y, we're going to follow these rules regarding t. Sometimes they tell us exactly what values to use for t. Sometimes they don't, and we just have to pick some values. It won't have endpoints if they don't tell us what values to use. This particular one says use t values from -3 to 1. There are actually infinite values between -3 and 1 if we broke it down smaller and smaller and smaller. We're kind of lazy. We're just going to use the integers from -3, -2, -1, 0, 1. Right, how are we going to calculate our x values? We're going to square the t and subtract 1. Everybody see that right here? Okay. So -3 squared minus 1 becomes what? 8. -2 squared is 4, minus 1 is 3. -1 squared is 1, minus 1 is 0. -1 and 0. Did I get that right? All right, how are we going to calculate y values? It says 2 times t plus 5. So make sure you're not using x, you're using t here. 2 times -3 is -6, plus 5 is -1. What would a -2 give us? 1? Because it would be -4 plus 5 is 1. -2 plus 5 is 3. 5 and 7. Did I do those right, guys? All right, what are we actually plotting on the graph? The x, y ordered pairs, okay? T is how we got those values, but we don't actually plot t on the graph paper. So we have 8, -1, 3, +1, 0, 3, -1, 5, and 0, 7. Our book asks that we attempt to indicate orientation or direction. So we're supposed to put some little arrowheads on here to show that we were going this way and then we curved back this way. Okay, mine's kind of hard to see. Because we were given restricted t values, there are actually endpoints. When t is -3, we had an endpoint of 8, -1. And when t was at the other end here, the other restricted end was at 1. So we have 0, 7 as an endpoint. All right, if we want to use our calculator, we're going to have to type these rules in. We're going to have to set a bunch of stuff in our mode first. I'm going to write this down before I do this. What was our restrictions on t, guys? When we go to put the window in, we're going to go -3 to 1. And we discussed that a t-step of 0.1 is usually pretty good. We'll talk later about not using 0.1, and I'll talk about why at the time. But x values, I was really lazy, and I just said, well, the graph paper goes -10 to 10 and -10 to 10, so that works for me. All right, so what you do is you go to mode on your calculator, and I'd like everybody to do this because I'm going to have you set some other things that we need for later in the lesson. All right, we're going to need degrees later today, so if you'd make sure you're in degree mode. And then this is the one that will get us the ability to graph in parametrics. We have to not be in function, but we are in parametric mode. Okay. And then we want connected and simultaneous graphing, because I'm going to show you later 2 different graphs and I want them to do it at the same time. And everything else is good. We okay? We got that set how we want it? All right, then we're going to go to y equals, which no longer says just y equals. It has some crazy business. All right, it says x in terms of t. Well, that wants a rule for x in terms of t, which is t squared, which when you hit the x button now, it's going to give us a t because of the mode we're in. T squared minus 1. Then we're going to scroll down and type 2t plus 5. We're going to go to the window, and you have to assign a t value. We were given one of -3 for the minimum, 1 for the max. Going to leave this 0.1. And I'm going to do -10 to 10 for my x's by 1, and -10 to 10 for my y's by 1. And it should look just like what we sketched on the graph paper. Any questions? Anybody not get it to work? All right, I just want to show you what happens. Remember I talked last week about if you change the t step, for example, to 1, it's going to plot values from -3 to 1 and connect them with a straight line. This is such a small graph, you can't really tell. I guess you can tell it gets a little pointier here. It's not really a smooth curve. But if I told it to only calculate every other number, like every 2, then you don't even get the whole thing because it calculated at -3, -1, and 1 and connected those. Okay, so this is kind of odd to us that we have to tell it how often to find a value and graph it. If we put something really tiny in here, and I'm not suggesting you do this, watch how slow it graphs, okay, because it's calculating 1,000 values in between there. Okay, so if you get it doing something like that, just hit on and clear and it'll quit. Okay, any questions? All right, the second thing we learned on Friday was we talked about eliminating t. Eliminating t meant writing it in rectangular form. We can change this to say t equals and substitute it into this one, or the other way around. Anybody have a preference? Okay, I would have chosen the y as well just because I don't have a square root then. So I'd go y minus 5 equals 2t. So y minus 5 over 2 is equal to t. Everybody okay? But I'm going to put that in here. So it will say x equals y minus 5 over 2 squared minus 1. I substituted it in. All right, I'm going to, and you could stop right there and I would accept that on the homework or on the quiz. If it said you had to have it in conic form or something, you would add the 1 over to this side, and it says square the top and the bottom of this fraction, and a 2 squared is 4. So if I multiply the 4 over to the other side, does this look like the form we dealt with all the last 2 weeks? That's a parabola whose focus and directrix have a p-value of 1 unit away from the vertex. Its vertex is at -1, 5, which is this point right here, right? Seem okay? All right. Now we get some crazy business. These were on your homework, and I did not choose to assign these until today. Notice we don't even have a t. Okay? It says over here, when graphing parametric equations on a calculator, theta and t are interchangeable. So we're going to type this in as x equals 2 cosine t and y equals 4 sine t and see what happens. But because t is actually theta, and I told you to put your calculator in degrees, if we want to see a complete graph, we're going to set our t window to be 0 to 360. Now, do we want to leave our t step as 0.1? It's going to calculate 3,600 things to try to graph then. Okay? Probably it would be okay. It would get done eventually. You could leave 1, so it would calculate 360 times. You could say I only need it every 5 degrees. That's what I did. I just wanted it to go kind of fast. And then for my X and Y window, I just cheated and went with the graph paper goes from -5 to 5 and -5 to 5. So I'm guessing it's going to fit. All right, so type all that in and see what you get. So 0 to 360 by 5 for my t-step, and -5 to 5 by 1 and -5 to 5. What'd you get? An egg? An ellipse? What do you notice about the ellipse? What is its domain? -2 to 2. Domain is least to greatest, the x values, right? What is its range? -4 to 4. Do those numbers seem familiar at all? Okay. Just to play around for a second, if you went in here to the window and you told it, I only want you to calculate every, I don't know, 45 degrees. Look what happens. Okay, it's no longer a smooth curve. If you only said every 60 degrees, it only calculates 6 values and connect them. Guess what you get? Nice hexagon. Okay? If you tell it, 1 degree, it's just going to go slow. All right? Does that help you understand a little bit better what the t-step is doing? It's how often the calculator is plotting those, calculating and plotting. All right. Before I try to explain how we eliminate t on this, let's sketch it. -2 to 2, -4, 4. And then I want to review something with you really fast. Do you remember even back in Algebra 1 doing these? X plus y equals 1, x minus y equals 4, 2x equals 5, plugging it back in, finding an xy. Remember that where we added 2 equations together to make a variable drop out? That has something to do with this question because there is no nice way to solve this for t or this for t, and even if we did, how do we eliminate the t? Okay, students always do things like x over 2 inverse cosine something something. Okay, not so much. What we're going to do is we're going to get x divided by 2 equals the cosine of t, and y divided by 4 equals the sine of t. And then we're going to use a little trig magic. We're going to square both sides, because squaring both sides of an equation is allowed, okay? Just like adding or dividing or multiplying or subtracting. Now what? If I add these 2 equations together, what will happen? I'll have cosine squared plus sine squared, which I could throw away and get 1. All right, so I have an x squared over a 2 squared, which is a 4, plus a y squared over a 4 squared, which would be a 16, equals a cosine squared plus a sine squared, which I'm going to cross out and replace with a 1. So it's x squared over 4 plus y squared over 16 equals 1. Does that seem to match up with this? A is 2 in the x direction, or I don't know, was A the biggest one of these? I always forget. A was 4 each way in the y direction, and B was 2 each way in the x direction with a center of 0, 0. Got it? Confused? Try these two. Anybody get x squared over 9 plus y squared over 4 equals 1 for the first one? So that one would be longer this way, right? Skip steps. Anybody get y squared over 16 plus x squared over 25 equals 1 on that one? Is that one longer horizontally or vertically? It goes out to 5 this way and 4 this way. It's actually pretty round, right? 5 one way and 4 the other. Not like my picture. All right, any questions on that? That's not hard if you remember how it works, okay? It's pretty hard if you don't remember what we did. Because you're not going to just look at that and go, oh yeah, I'm going to divide and then square it and then add it to the other one. It's just kind of a little magic trick. You okay? All right. This is just kind of a demonstration of something nice that parametrics do. It's not something that's on the homework. We're going to graph inverses real quick. Does anybody remember what an inverse is? Remember when we had like y equals 2x minus 4? You switched the x and the y, and then you solved for the y. And then this was the inverse, or we used some weird notation like that. Do you remember what happened when you graphed those? One of them was doing this. What happened to all the ordered pairs? They switched, so it wound up doing this, and they were a reflection across the line y equals x. Does that sound familiar to somebody? I would like to think so. All right, we're going to graph this. It says to use negative 10 to 10 for t. Actually make negative 10 to 10 your x and y as well, okay? So everybody start typing. Put in these two equations for your y equals. Three t minus 1 and a t squared plus t. And make your window negative 10 to 10 by 1 or 0.1. It really doesn't matter. And then negative 10 to 10 for x. And negative 10 to 10 for y. And hit graph. So you get a great big wide opening up parabola. I'm actually going to do a zoom square so that it's not stretched. Funny, all that does is change the scales. So if you look now at the window, it says x actually goes negative 15 to 15 and y goes negative 10 to 10. That's because there's more, our rectangular screen is longer this way. So it's got a more of a 1-to-1 ratio. All right. Anybody think they know how we're going to graph the inverse? You got it. This is the easiest inverse you're ever going to have to do because all you have to do is switch the rules. The x rule is going to be t squared plus t. And the y rule is going to be 3t minus 1. There's no working backwards. There's no doing anything crazy. You're just flip-flopping them. Hit graph again. Does it seem okay? One had its vertex over here. The other one has its vertex over here, and it's going this way. They're actually touching. Mine just aren't touching because I did a really bad sketch. Try number 4. Leave your window the same. Type in the rules for number 4 and type the inverse. So the first one is a really scrawny little half parabola or square root graph going from the left of the screen to the right. How do I get the inverse? Okay, I have to flip-flop the rules. Somebody typed it in the same way a second time last period. If you don't flip anything, it doesn't do anything, okay? You got to flip the x and the y rule. So one was a little skinny graph going this way, and the other one's going this way. Everybody good? So the inverse had this. So you understand how you do an inverse? All right, number 5 is a Hofbauer wants to show you this because she thinks it's cool question, okay? Do you remember when we did problems like this right here? Everybody see what I'm talking about? We had negative 16t squared plus 90t plus 5. This would have been the initial velocity was 90 feet per second, and the initial height was 5, and we're throwing the ball straight up in the air. We wanted to see how long it took to come back down or how high it went or whatever we wanted to find out. All right, I want you to type all this in. Put in x equals 8. I'll talk about what that 8 means in a minute. Put the rest of this in your y and set your window to what I've written over here. Okay. Yes. You're fine. Is that the least exciting thing you've ever seen? Yeah. There's a little vertical line over there. Wasn't that exciting? Okay. The x equals 8 that we put in made the vertical line be on x equals 8. If we put in x equals 2, it would move that same exact stick over to the 2. I put it over there because I want to show something else on the left side of the screen in a minute. Before I do that, go back to your x equals, your y equals button, sorry, arrow to the left until you're in front of the x, and then hit enter twice so that you have the little thing that looks like a -0. Okay? The bouncy ball, I like to call it. Now, watch very carefully what happens on your screen when you do that.
Whoa, bouncy
the ball goes up, and the ball comes back down. But something more important happened. Did anybody notice what happened? It did go underground somehow, right? Because we put too much time on there. That's okay. Did you notice anything about the bouncy ball? Watch mine one more time. What happens as it gets up to the top? It slows down and stops. And what happens as it approaches the ground again? It gets faster. It's accelerating. Is that real life, guys? Okay, that's physics, right? When you throw the ball up, gravity causes it to accelerate as it comes down. It actually has an instantaneous speed at the very top of 0. All right. Yeah, you have to change. If you go back and change it to the bouncy ball with the stick behind it, or the so it says -0 or just this. All right, guys, just to show you this because it's kind of cool, go down into x sub 2 and type in what it says underneath here. Don't change your window or anything, but type in for x sub 2 a value of t, and for y, oh, what did I do? This isn't turned on. For y, I'm going to go -16 t squared plus 90t plus 5. Okay, now because I said for x to be t, it's actually going to show the parabola that we talked about back in chapter, I don't know, 2 maybe. All right, if you watch mine, I have the bouncy ball turned on for both. Watch what happens simultaneously. Oh, I have something typed wrong. Yep, way wrong. One went higher than the other. All right, what did I do? -16. Oh, t to the -1. What's that all about?
You hit the wrong button instead of hitting the power.
It's because I can't see that. I can't see these buttons on because I'm blind. I did it again, didn't I?
Yep.
Is it this one? Oh, yeah, except I got it in the wrong spot.
You have to hit 2, not squared. That's squaring. There you go. Oh.
All right, let's see. Try it again. There we go. So this is showing you the path that we normally would have thought about as that parabola. And it's showing the actual path of the ball, which is straight up and back down. Okay, could we find how high the ball went, how long it took to hit the ground, etc., etc.? Okay. This was just a humor Hofbauer because it's really cool to show you that thing. This is even less exciting. So you can do this one if you want. If you don't even want to do this one, I'm going to go quickly because I want to get to the homework ones. This one says we have a ladybug. She's flying along on the graph. Jacob's scared of ladybugs? Really? I am going to change my window a little bit. It says along the line y equals 3. So y is just y equals 3. I'm going to leave 6 seconds. But she actually goes a little bit further left and right. So I'm going to go -20 to 20 for my x. And my y I'm going to make 0 to 10 because she's just going to stay on 3. All right. I'll turn on the bouncy ball path for you. Here you go. I'll do mine first, and then you can watch yours. Here's the ladybug. Oh, I didn't change my window. It's, silly me. All right, this should be 0 to 5, maybe. Okay, one more time. Here she goes. She goes to the right, to the left, and then she takes off to the right and goes really, really fast. Okay? If you trace along, I need you to understand that all you can control is t. You can go forward and backward in time. That's it. You have no control over the x and y. So if you want to know when she turned around, you're going to have to watch the x and y values. If I go back to time 0, okay, here's where she starts, time 0. Right now she's at -10. Now she's at -9.2, -8.4. She gets to -6, and then she goes back the other way. What time was that? Anybody figure out? Yeah, it was lunchtime. It was at t equals 1 she turned back around. Can anybody figure out where the other time she turns back around and goes off? Yes. At t equals 2.9, she's at -9.88. Then she's at -10, and then she's back at -9.99. So at 3 seconds, she turned around again. If you type 2, at 2 seconds, if it was in seconds, I'm just making that up, she was at -8.3. All right, again, that was fun, not a question off the homework. These are the questions off the homework. We talked about one of these on Friday. When you have an object launched at an angle to the horizon, so not straight up, but at an angle, much more realistic most of the time, okay? Other than a pop-up that the catcher catches, how often do we hit or throw something straight up, right? Not very often. All right. We have x equals t times initial velocity times the cosine of the angle, and y equals, and the y is actually equal to this, guys. It's -1/2 gt squared. As long as we are in feet per second, when you put a 32 in here, you get -16. Later on, we're going to do a question that has 9.8 meters. So if you're in meters per second, -1/2 times 9.8 is actually -4.9 t squared. Okay? I gave you that on your paper, didn't I? A little box about that. And you need that for these two homework problems. They are in meters per second, not feet per second. All right. Here's our question. Manuel launches a toy rocket from ground level. So what's our initial height? With an initial velocity of 80 feet per second. So that tells us two things. V sub 0 is 80. And because it's feet per second, our gravity is 32 or -16 t squared. All right, at an angle of 80 degrees with the horizon, horizontal, that's our theta. Now, I wish it wasn't 80 and 80. I should have changed this question, but it is, so we're going to live with it. X equals, what does the equation say from your notes? T times V sub 0 times cosine of the angle. Y equals, just lost my cursor. It's -1/2 of 32, which is -16 t squared, plus t times 80 times sine of 80 degrees, plus initial height, which is 0. All right, what's an appropriate window before we try to type this in? How long do you think it's going to take to hit the ground? We'll go 5 seconds?
Yeah.
Okay. How far away do you think it's going to go? 75?
Let's do 74.
And how high do you think it's going to go? All right. I don't know if that's appropriate or not. We're going to try it. Type. Beat me. Come on. You can do this. Remember, it's sine on the y. All right, my window, 0 to 5 by 0.1, 0 to 75, because that's what John picked, and 0 to 100. That is a beautiful window. I don't know if you guys already tried this out or what, but that's gorgeous. All right, I am going to change one thing. I'm going to change my y min to like negative 25 or 50 or something, just because then I can see when I do my values. Ooh, our time is even good. Look, it stops right after it went underground, right? All right, let's see if we can answer these questions. How long will it take the rocket to travel 10 feet horizontally? What does that mean? Horizontally is across. So x is 10. So I need to go trace forward in time until x is 10. Can you hit exactly x is 10? You can, probably. But it's somewhere between what? The only thing we can change is time. Somewhere between 0.7 and 0.8. Now we could break that down. We could try 0.72. Oh, that was pretty close. I might have known that from another class. Okay, so 0.72 seconds is pretty good because it gives me x is about 10. What is the vertical distance up in the air at that point in time? Now, because I didn't get exactly 10, these are estimates. If you had between 0.7 and 0.8 seconds, it hit around 10 feet away from you, and you had a little different answer here for the up, I'd have to accept that, okay? What is the maximum height it reaches? Anybody figure that out? What are you looking at? Yeah, I got 96.96, the y value, right? So around 97 feet. And how far away does it land? What do we got to do there? Yeah, until it has a y value of about 0. 4.9 is close. I don't know, 4.91. Does that get us closer? .92. .93. I don't know. What gets us closer? 4.925. There, it's got a 0. It's right around 4.9. About 4.92 something seconds. But that doesn't answer the question. How far away does it land? 68 point something feet, right? All right, we're going to do the last one, the golf guy. What is different on this question that we have to notice?
Stars.
There's stars and there's a picture. The reason is it's meters. So x is still going to be t times what's initial velocity? .56 meters per second times the cosine of 12. What's y going to be, though? It's negative 1/2 of 9.8 because it's meters per second, which is negative 4.9. t squared. You could type negative 1/2 of 9.8 if you want. Plus t times 56 sine of 12. If it's a golf ball, is there an initial height? Not really. Especially if you got a divot, right? Okay, we could add 0.0 something. It's in meters, so I'm thinking it'd be, what, 0.02? Would that be 2 centimeters off the ground? All right, guys, are you typing? What do we need to change our window to? What? I don't know if 6 is enough. It might take longer for the ball to come down. Six might be enough. 7 seconds, I don't know. These are meters, so it's going to go far away, but I don't think, like, meters correspond to yards. I don't know, 300, 250, what do you think?
625.
The y is the height. I don't know, it could leave it 100. I'm pretty sure it's not going to go that high. Oh, no. I didn't need that much x or y or time. Okay, I'm going to change that back to 150. And all right, whatever. As long as you can see it in the screen, you're fine. How far away will it land? What do we want to know? Which value do I want to write down? The x value when the y value gets as close to 0 as we can. I got about 131, about 2.4, 2.3, I don't know, I'm guessing 8. What do you think? 2.38 is really good. So 130 point something, between 130 and 131 meters. Someone else get that close?
Yeah.
Okay. All right, so you have some application problems on your homework. This is the assignment you need to work on. I wrote you a little note here. When you do 45 through 48, they're matching. I put my calculator in radian modes and did 0 to 2 pi, and I made some really fun designs and fiddled around. What you want to do is change some of the values. We'll spend the first 5 minutes playing with those tomorrow while we eat our Pi Day cookies. How's that sound?
Yeah.